everybody. Thanks for joining. So today I'll be talking about our publication with the title Improving Prostate Cancer with Breast Histopathology Images. My name is Oguzhan Gencoglu. I'm the third author. Interestingly, our authorship order is it's not based on the length of our names, but it turned out to be like that. I just noticed. But there are two main partners in this R&D collaboration. Helsinki University Hospital from Finland. Tuomas Myrtti over there, Professor Doctor, he is leading the medical side. And I'm leading the AI side from the startup called Top Data Science. Shortly, we provide machine learning as a service, so we are not a single product company. We are good at solving problems with machine learning, and our clients and partners are good at having problems. So it's a good match. And quick announcement that in the book of abstracts, actually there has been a small error. This abstract doesn't belong to us, so just to clarify that. We have noticed that there has been an error and notified the organizing committee. All right, my outline will be, I'll talk about our hypothesis and motivation behind this transfer learning method. We have fairly simple, from the deep learning side or machine learning side, fairly simple methods, and I will a bit elaborate on future work and our results. So our motivation is that life is too short to annotate lots of whole slide images, and we want to let other people do it and focus on smart algorithms to use those annotated images in certain domain to improve our domain. So we don't want to do this. And our hypothesis is based on quite simple observation that breast histopathology images, breast tissue images, are more similar to prostate tissue images visually compared to images of cats and dogs and wine bottles. So it's not an outrageous hypothesis. It's not like we claim prostate is made out of cheese or something. But the point is that basically, consequently, we hypothesize that breast tissue images are better pre-training material for prostate cancer detection than ImageNet or these kind of natural images. So our methods, our data is obviously ImageNet, except that we haven't trained an ImageNet classifier. Like, who does that? So we got a pre-trained model. So if you're not familiar with ImageNet, it's like the data set, more than 1 million images of all kinds of objects, 1,000 categories, and there are pre-trained models as open source. But for the breast tissue images, we have used Chameleon 16 data set. So it is open to public, well annotated, and it's a large data set of 110 whole slide images. And we have our own actual problem data set of prostate histopathology slides, 28 slides from Helsinki University Hospital. Both are H&E stained. So we have our pathologists' annotations as well as the basically, these annotations are pixel level annotations with polygon markings. So we can create a binary mask and turn this problem as done in a standard way into a binary classification problem of small tiles. So we can sample benign and cancerous regions out of this. Pretty straightforward. Our model is based on Inception version 3 algorithm. So the kicker is that you need to use the convolutional backbone as a pre-training so that we remove the dense layers at the end. So we add our own dense layers with rectified linear unit activations and dropout rate of 0.8. Then the output layer is simply sigmoidal. We try to minimize binary cross entropy with Adam optimizer with 10 to the minus 4 learning rate. And we run our algorithms for 50 epochs, and of course we get the model which performs the lowest validation error. So we trained 3 models. No pre-training means we trained with our own prostate tissue prostate whole slide images. It means the neural network coefficients are randomly initialized. Then we use ImageNet pre-training and breast tissue pre-training. So basically, this is training from scratch with our prostate whole slide images, and these two models are fine-tuned with our prostate whole slide images. So experimental setup, chameleon pre-training, the breast tissue pre-training consists of 110 whole slide images, meaning millions of samples of tiles, those small tiles I have mentioned. And our data has 28 whole slide images, 22 of them basically used for training, and six patient cases are totally separate for testing. So basically, the testing is tile by tile predictions of these 6 whole slide images out of the trained models. So there are millions of our results, which I'll be showing soon, is based on millions of small tiles out of this 6 held out test set. Okay, so this is the kicker. When you don't do any pre-training, our AUC score, area under the ROC curve score, is around 0.87. ImageNet pre-training improves it as expected and has been shown many times, but the thing we have proposed is pre-training with breast tissue images improves it further. We have also detailed analysis of slide-by-slide scores. We also give pixel-wise AUC scores in our paper. So one visual example is that this is a test case that the model hasn't seen. This is the region, annotated the ground truth region, and this is the heat map, probability heat map prediction of our model. Some remarks. So basically, there's this study is yet another evidence that ImageNet pre-training, it's a nice baseline. It works if when done properly, but we try to propose something new. And one thing I would like to emphasize is that the whole point of this study was not to maximize these numbers, because there are like a plethora of tricks what you can do, right? You can do architecture search, hyperparameter optimization, you can do data augmentation, hard negative mining, ensemble of models to make this closer to 1. But that's not the point. So the point is this relative difference. So this is still future work. So on purpose, we wanted to isolate this effect of transfer learning from another cancer domain. So I'm finalizing. Key takeaways: transfer learning is a powerful tool. Use it. ImageNet is a valid baseline, but we provide the evidence which needs to be validated, of course, with several other cohorts, evidence of cross-cancer pre-training over ImageNet. And we also believe that this also increases generalization ability. So because different kind of whole slide images are scanned with different machines or settings, have different staining. So if we can provide such a setting that several cross-cancer images are pre-trained together, hopefully this will increase the generalization ability of learned models. Thank you very much. This was my talk.
So thank you very much. Any question? Yes, please.
Yeah, thanks for an interesting talk. I was just wondering if the end result is actually better with the chameleon initialization, or is it just a matter of faster convergence? So if you trained longer on the ImageNet initialization, would you be able to match the chameleon?
So basically, no, because we have got the model that had the lowest validation error. So the duration of the training was independent of the final model, because we don't take only the final training, and we of course stop it after it stopped actually improving.
Okay, thank you.
Yes.
Very interesting presentation. Obviously 0.92 is larger than 0.90. Is the difference statistically significant because your data set is relatively small? Also, did you look at the tiles? Which tiles was it really doing better when you trained with Chameleon versus the other?
Thank you. Let's start with the first question. So these results are the results of millions of tiles coming out of these 6 test sets. So this number 6 is small indeed, but these are tile-wise results. So as you said, we still have to run this several times indeed to get statistical significance, but just to give the idea that this is very, very less likely that it's just by random, because this is out of tile-wise AUC score. And for the second question, we have visualized by basically comparing those two models, and the false positives were less. So these firing ups were less.